electron 1. Okay, so today we talk about the unrestricted Hartree-Fock theory, and till the point where we worked out the operator equation for determining the spin orbitals, we did not make any extra assumptions about the determinant or the state that we were dealing with. But after this, when we went from spin orbital to spatial orbital, I said we were going to do only restricted closed shell functions. And that meant that we're only going to treat systems with even number of electrons where all electrons were paired. And that is called a closed shell system. So we made this assumption, which meant that every spin orbital is written as a product of a spatial part and a spin part. Okay. So if this is the alpha spin orbital, then the corresponding beta spin orbital for the beta spin ith orbital has the same spatial part but a different spin part. So this is what was called restricted. Now, I had also mentioned then that if it was unrestricted, then I would have chi I equal to, let's say, psi I alpha, and chi I, and then this you would not call chi I bar. You would, so it's not just, you can't use this notation. So you would call it maybe chi j or chi I prime. I don't know what to call it. Let's say, let's call it chi j. So this would be psi j beta. So here, even though you have approximate pairing, you don't know a priori whether they will actually turn out to be have the same spatial part or not. So you allow the spatial parts to be different for the alpha and beta spins. Now, after the optimization, it may turn out that the spatial parts are the same for a pair of electrons, but you let the wave function have the flexibility. So in case they are different, they can be different. Okay, that is what is called unrestricted. If you are not very particular about notation, you can also say chi I bar is equal to psi I beta. Okay. But when you have unrestricted orbitals, your spin orbitals are simply labeled 1, 2, 3, 4. So it's not 1 bar, 2 bar, because 1 and 1 bar have different spatial paths. So just be clear about what they mean, even if the notation does not always reflect all the details. Okay, so in that case, okay, and why do we need this generalization in the first place? So one obvious reason is you can have open shell species, open shell molecules. The oxygen molecule, a radical, okay, even the hydrogen atom, okay. So these are all open shell molecules. So here there are odd number of electrons. So they are by construction open shell, and here you have even number, but it's still triplet. So this is also an open shell. And in these cases, if you say that your wave function is such that every orbital is doubly occupied, every spatial orbital, that is simply wrong. You cannot describe open shell systems with a restricted description. So what shall we do? So can we derive the Hartree-Fock equations for the unrestricted function? Actually, it's quite straightforward. It follows exactly the same steps as the restricted derivation, but there are some subtle differences which I will point out as we go along. So first things first. So let's see. So
Ma'am,
now, yeah.
what have you written in the upper part of the CH3 and hydrogen?
Oh, I've just put a dot for the electron, so it's like
Oh, okay.
radical. I haven't
Okay.
written anything. So CH3 radical, that is what I meant, and hydrogen atom has one electron. Okay. So so basically, since you have two different sets of spin orbitals that you want to describe, so let's say chi I alpha, the spin orbitals for the alpha electrons, and you have another set chi I beta, which are the spin orbitals for the beta electrons. And you need to determine the two sets in some sense separately. So you have two operator equations. So since this operator equation is general, whether it is restricted or unrestricted, we have not made any assumption till we derived that. So now we can split that equation into an alpha equation and a beta equation. Okay. So notice that even the orbital energies are allowed to be different, but they may turn out to be the same. Okay. Then that is fine. So there's no big deal. But what is F alpha? So F alpha, we can actually write by thinking of the physical considerations. You can derive it rigorously as well, but this is easier, you will see. So you have the one electron part, which does not depend upon whether the electron is alpha or beta. It is just the kinetic energy and the nuclear attraction. That has no alpha or beta label. Then, so what does the Fock operator represent? It represents the interaction of electron 1 with the other electrons. So now if we talk about the other alpha electrons, then the Coulomb interaction is there with the other alpha electrons. So you have the Coulomb operator. With the other alpha electrons, since electron 1 is an alpha electron, you can also have exchange interaction. Okay. So I can write this as well. So this takes care of the interaction of electron 1 with the remaining alpha electrons. Now for the other beta electrons, then you do not have exchange because alpha and beta electrons cannot have an exchange interaction. Then you only have the Coulomb interaction. So there is only a slight difference between the F alpha and the F for the restricted case. Similarly, I can write the F beta, and here this will be N beta, with which you have both Coulomb and exchange, and the beta electron can only have Coulomb interactions with the alpha electron. Okay. Fine. So that's it for the Fock operator. But these are still in spin orbital basis. So we have not gone over to the spatial orbital basis yet. And what you need to do now, of course, is to write all these quantities, so J and K, so as products of space and spin, and integrate the spin. So I'm not working it out now because it will take a lot of time, but it's straightforward. So what you need to find out is, of course, things like psi I alpha, F alpha, psi, sorry, chi, I should write chi. Chi I alpha, then you can have chi I beta, etc. Okay, then you write the chi as psi into alpha or psi into beta. Then you integrate the spins, and you will end up with the expression, with the expression of the Fock matrix in spatial orbitals. I guess you can see that it will work out. You have to just do the algebra. Then, and once you do that, you will see that the matrix elements of the H, or the one electron part of the Fock operator, that is the same as you would expect. Okay. So the expression is the same, is what I mean. So it's not, so the value is not necessarily the same, but the expression is the same. And also the expression for the GII alpha, GII beta beta, okay, GIJ alpha beta. So all these expressions you will get in terms of spatial orbitals, and they are exactly analogous to what you have got as expressions in the restricted case. Only there you wrote psi I or psi I, psi j, and now every time you will have psi I alpha, psi I alpha, psi I beta, psi I beta. So even the so the number of integrals do not get reduced. So when we went from spin orbital to spatial orbitals in the restricted Hartree-Fock case, my summation went from I equal to 1 to n in spin orbitals, and then it went to I equal to 1 to n by 2 spatial orbitals. But when for the unrestricted, this is for the restricted Hartree-Fock. But for the unrestricted Hartree-Fock, your sums which go from I equal to 1 to n for the spin, they go to I equal to 1 to n alpha plus I equal to 1 to n beta. So effectively, you don't have any reduction in dimension, but the expressions are the same. The energy expression, of course, looks again slightly different, like the Fock operator. So there you have this sum A equal to 1 to n alpha, H alpha AA, plus A equal to 1 to n beta, H beta AA, plus you have, okay, I'll write it on the next page. That's not so good for today. Half of sum AB, which is a double sum going from 1 to n alpha for the both alpha. So when both the electrons which interact are alpha, you have both Coulomb and exchange. Similarly, you have both beta beta. So those, that looks exactly like the restricted Hartree fork. But then you have the extra interaction between, so A equal to n 1 to n alpha, B equal to 1 to n beta, and there you have only the Coulomb interaction. It's quite easy to see how the physical interactions change a little bit, giving a slightly different energy expression. It's not marvelously different. Okay. Then after that, of course, you have to go over to the matrix equation. So when we went over from the operator equation to the matrix equation, we introduced a basis set, and the matrix equation we obtained in the restricted case were called Rutan equations. For the unrestricted case, the idea is the same. We will introduce a basis set and go from the operator equation to the matrix equation. The equations in this case are called Pople-Nesbett equations, because they were the ones who first derived it. And there's only one thing to note in the basis set expansion of the spatial paths of these unrestricted orbitals. That is, k is the size of the basis. The basis functions still remain independent of alpha and beta. They are the same, but the combining coefficients, these are dependent on the spin that is associated with this spatial wave function. Okay. So the basis set is replicated. So you have psi I alpha, and psi I beta is also described by the same spatial basis set. So these are just the Gaussian functions or contracted Gaussian type orbitals that we have been talking about. The combining coefficients are dependent on whether this is the spatial part of the alpha electron or the spatial part of the beta electron, and I is k orbitals. Okay. And when you do this, you will get very similar matrix equations. For the alpha and the beta part. Now, what is the important thing to note here? So, these are two separate equations. So, are they independent of each other? That they are not, because the Fock operator for the alpha electron contains the orbitals of the beta electrons. So which means that although they appear as two separate equations, they are coupled. So you must solve them together. So you solve one equation, you obtain the orbitals. Let's say you solve the alpha equation, you get the orbitals for the alpha electron. Then you can use those orbitals to construct the Fock operator for the beta electron, and you solve the beta equation. And again, with those new alpha and beta orbitals, you reconstruct the Fock operator for the alpha electron. So they are coupled equations and must be solved together. So the method of solution is somewhat different. So in the restricted theory, you only had one equation and only one diagonalization was involved and that could be iterated. But here you have two, so you have some sort of nesting of the operations, of the matrix operations in your code. Okay, and here remember these Fock operators, these are of the type mu nu. So this matrix is in the basis. Okay. And before we see what exactly goes into F mu nu in what form, that we have to look at, because it's a slightly different, right? Because the coefficients that go into so since this is a matrix operation in the basis, and the basis is the same, the only source of dependence of the alpha equation on the beta equation is from the C's. So you will have a set of C's which go into the definition of F alpha. And if you remember from the restricted case, we had defined a density matrix which was of the form CC star, and that is what the Fock operator or the Fock matrix depends on. So in this case also we will have density matrices. So let's see what they look like now. So unrestricted density matrices. I will need 5 more minutes. So unrestricted density matrices, and these are defined again analogously. So the density function of the alpha electrons is simply sum over all the alpha spatial orbitals psi a alpha r mod square. Okay. And similarly for beta, I'm not writing it for beta. Okay. And you can have a total density function, which is simply the sum of the alpha density function and the beta density function. Okay. And when you integrate the total density function, of course, you get the total number of electrons. So this is, and the form of the density matrices. So these are the density functions. And what we write as P is the density matrix. This also has an alpha electron component and a beta electron component. So the alpha electron component, the mu nuth element, is then why does it go? Come on, scroll. Is equal to a sum over all the alpha orbitals of C alpha mu A, C alpha nu A star. Okay. So that is the definition, and similarly you have a beta spin matrix as well, density matrix as well. And I can also have a total density matrix, and that is P alpha plus P beta. Okay. Now, the additional thing that is interesting in the unrestricted case is you can have an idea of the spin distribution in a molecule. So you can define something called a spin density, and that is simply the difference. So let's say this is the spin density function, and this is a difference of the alpha density function and the beta density function. So if you have an excess of alpha electrons in some region in a molecule, my spin function will show a positive sign. And if you have an excess of beta electrons in some part of the molecule, you will have a negative spin density. Okay, and if you have a zero spin density somewhere, it will tell you that the electrons are either all paired in that region or absent from that region. So two options if the spin density is zero. And again, that is the density function. You have correspondingly a spin density matrix. And that is the difference of the spin density matrix of alpha and the spin density matrix of beta. Simple enough. Okay. And then I told you I will come back to what goes into the Fock matrix. So let's look at one element of the Fock matrix for alpha spin orbitals and open out the integral. I will just do one, okay? Don't worry. I'm tired of writing integrals in every class. Okay. Then you have the H core mu nu part, just like the restricted picture. And you will have then a sum over the alpha molecular orbitals. And you have the this is alpha alpha. So I'm talking about the Fock matrix of an alpha electron. So I have a Coulomb integral, and I have an exchange integral. And the beta interaction of the alpha electron with the beta electrons, and that has only the Coulomb. Okay. And as you can see here, you have the basis functions, which have no alpha beta dependence, and you have the orbitals, which depend on alpha and beta. And when you open out these molecular orbitals, unrestricted molecular orbitals, you will get the C star quantity here. And then you will end up with the Fock matrix as a function of the density matrix. And X core mu nu plus a double sum over basis functions of a total density with a integral over basis functions minus a sum over lambda sigma p lambda sigma alpha. and then integral. So what is this extra integral? This is the extra exchange integral. So since the Coulomb is present for both alpha and beta, those can be summed up to give the total density, and the exchange that the alpha electron experiences with other alpha electrons, that appears explicitly. Okay. So that is it about the unrestricted solution. Now let me tell you something about what can happen when you solve these unrestricted Pople-Nesbet equations. So what can happen is that since you allow the spatial paths to be different, they may turn out to be different. But most commonly, if you are solving a closed shell molecule, like say lithium hydride, with an unrestricted Hartree-Fock method, you would still end up with the same orbitals as the restricted case, because there the electrons really do want to be in the same orbital. So they want to be paired up completely. So the unrestricted calculation will reduce to a restricted calculation numerically, even though you have not imposed that. However, if you are doing a calculation on an actual open shell species, like say I think in the book the example is CH3 radical, but it can be anything else. Okay, an oxygen molecule or even a hydrogen atom. Then physically also, since you have one unpaired electron, this unpaired electron will affect the alpha and beta electrons in the other orbitals differently, because this exchange interaction is present with the other alpha electrons and absent with the beta electrons. So there will be a differential interaction with the other alpha and beta electrons. So even though they are largely paired up, there will be some difference. Okay, and this difference cannot be caught with a restricted description, because there you are enforcing the pairing. So in that case, the unrestricted description is more natural for such cases where you have an actual open shell. Okay. Also for oxygen, it is a very obvious case. So experimentally, we know that oxygen is an open shell triplet. So if you had forced it to have a restricted description, it would simply be wrong. With the unrestricted description, you will actually get a proper triplet with the two unpaired electrons in the two degenerate p orbitals. But since these electrons are there, the other inner electrons, even the 1s electrons, the alpha 1s electron will be in an orbital that is slightly different from the orbital in which the 1s beta electron is. Okay, and you do not have an analogous molecular orbital theory like the tool where you analytically or by hand you say which orbital is occupied by which electron. So that is entirely based on a restricted description. You don't have a corresponding diagrammatic tool for the unrestricted description, but that is more natural, as you can see in case of open shell species. Okay, so that is one thing I wanted to say. The other thing is a little more technical, in the sense that even when the species is closed shell, so again, what we are doing is the same thing. We are computing a closed shell with unrestricted Hartree-Fock. Okay, then one solution for these coupled Pople-Nesbett. So I am doing an unrestricted Hartree-Fock for closed shell. Then one solution is that P alpha is equal to P beta, and this is what is the restricted Hartree-Fock solution. And this is most commonly obtained. However, if P alpha, you have another, it's a very bad handwriting, okay, P beta. However, if it may turn out that P alpha is not equal to P beta, even for the closed shell. So is this the correct solution or is this the wrong solution? Now, this we do not know perfectly. So what we do know is that if P alpha is not equal to P beta, then and that somehow turns out to be the solution with minimum energy, then this has an energy which is lower than the Hartree-Fock energy. And this is called sometimes the symmetry broken solution. Now, so in a usual sense, from the name itself, you can see this is probably a wrong solution in a way. But it has its uses, especially when you're doing dissociation dissociation surfaces. So when you're dissociating a closed shell species into open shell species, then you need to be able to describe both the open shell and the closed shell species equally well to get a smooth surface. In that case, a restricted description is not good enough. It will simply exclude any possible open shell solution. And you will get a very weird potential energy surface, which will simply keep increasing in energy as you move the fragments far apart, or it will simply fail to converge, like you must have encountered for LIH at the large bond distances. Calculation, then when your fragments become open shell, it will be able to do this. And in that case, even if you get symmetry broken solutions near equilibrium or in the intermediate stage. So in the intermediate stage, again, you don't know if the symmetry broken solution is right or wrong. Okay. But in the dissociation, if it gives you proper fragments, then that is the correct dissociation limit, if you get my point. So this may appear a little bit vague to you at the moment, since you're not doing computations by hand, but once you see it for yourself, you will realize that that the situation is like this. So when you want to describe a smooth surface, you have to accept that some intermediate region may be wrong. Okay. But if it's largely correct, you accept it. So that is what I wanted to say about unrestricted calculations. So do you have any questions from today or from previous classes? Do you all have any questions? No? Any question? Yeah.
Today, have you the expression that why P alpha is not equal to P beta, why it is less than RHA?
Why it gives RHF solution?
No, energy less than RHF energy. when P alpha
Oh,
at
okay,
the
okay.
last.
This is why it gives you less energy, because there are more degrees of freedom. Like if you give a variational theory any extra degree of freedom, it will go to a lower energy. Whether that degree of freedom is actually present is a different question. So if it is a if it is correct to give it that degree of freedom is up to you. But if you give it, then if you go, for example, the same thing, if you go to a larger basis set, your energy will always go down. But you can add very bad functions, for example, to a basis set, uh, and that may and that probably has little role to play in the physics of your system, but your energy will still go down, even if it is a little bit. So it's
And
because
then
it's yeah.
basis weight, then the basis set where number of bases are greater, there the energy I should expect that will be less.
Yes.
Which is same for and this LIH calculation. Like if someone using STO3G and someone using 631, then is a 631 case I should get a bit less
Less
value.
energy. Yes, yes, yes. Certainly. Certainly. So the more
Um,
degree of freedom you give to a variational theory, the lower the energy will go. So if you, yeah, yeah. So this is one thing. Similarly, if you like instead of saying that you use a single determinant, if you apply the variational theory to, let's say, uh, two determinants, a combination of two determinants, the energy will again go even lower. So the more restricted it is, the higher up the energy is.
and regarding the midsem, our midsem is already scheduled on 6th.
Yes, I saw that. Yes, it is scheduled on 6th. But that's okay, I guess. It's fine with me. No problem.
So will you continue the exam on the given time, that is 1 hour and 30 minutes?
Yes, that has been decided by the academic board, and we
Okay,
cannot increase or decrease the time. It will be 1 hour 30 minutes.
okay,
Strictly 1 hour 30 minutes.
okay.
And it will be
Tomorrow,
when we
and tomorrow is 1 hour.
Tomorrow is 1 hour, yeah.
Okay,
Tomorrow is only till before the basis sets. So I meant, I think section, yeah, before 3.5 or something.
okay. And midsem will be up to today.
Midsem will be up to today. Yes.
Oh, okay.
Okay. So fine.
how we are going to take the midsem is in we learn the same as class test.
Same as class test, yes. So Professor Pal and I did not opt for the proctored exam. So it will be just like the class test. It will be on VLearn.
And ma'am, I would suggest that it will be better that if instructors will be available online in at least one platform. Maybe WhatsApp is still okay because we may have some queries. Like in the last class test, we have some queries, but we did not uh, find.
Okay, okay. I will stay on. Is WhatsApp better or Google Meet is better? You want? I can switch on the Google Meet and keep it on. That will also be fine. Yeah. Then I will just keep the Google Meet on with the same link like our class.
Yes, the Google Meet can be an option that way.
Yeah. So you can keep it on. The only issue with this is I hope with your internet that will be fine. Like if you have Google Meet on and also the exam portal, if that does not create a problem for you, it's fine with me. Or I will stay on and when you
If
all have a
someone
question, you all join.
if someone have a internet problem, then if he or she ask on WhatsApp, is that fine?
Yeah. That is all. That is fine. That is fine. Last time actually I was a bit busy during that time, but this for tomorrow as well as for your midsem, I will not. It will not be a problem. It will be
Okay.
okay.
And and also the all the
Okay.
questions would be descriptive, right? Like the first class test or whatever will be tomorrow onwards. I mean, no MCQ for that case.
Tomorrow I have not finalized your question paper.
Okay.
I don't know. I think you can see that for this subject MCQ is a bit difficult.
Yes. Yes.
I can't think of how to give you MCQs.
No.
They will be descriptive, but short answers are perfectly acceptable. No problem.
Okay.
You can write point wise. You don't have to write sentences or anything.
Okay.
That's fine. And for the midsem, no. For the midsem, I will still give you some MCQs. Otherwise, you will not be able to finish the exam. So I will. So midsem will have both an MCQ section as well as some written part.
Yes, but everything is on pen and paper, right? You are not going to create other MCQ portal.
No, MCQ portal. It will be the We Learn MCQ portal in the quiz mode. So that I will have one part,
Oh,
and I will have a separate like a separate subjective question section, which will be in assignment mode. So the subjective questions you can submit as one file, and the MCQ you do on the portal. That is fine, right? Do you have a problem with that?
No. No. That's fine.
That's fine, right? Okay.
Yeah. Just if you are aware about the pattern, it is fine.
Yeah. Once I finish setting up your question paper, I will write an email because
Okay.
not everyone is in class, so I will
Yes. Yes. Yes.
email it. Then everyone will know.
Okay. Okay. Thank you.
Okay. Yeah. Thank you.